Hi to all. Today's topic is AC voltage applied to a capacitor. I am applying the AC source. I am connecting the AC source to a capacitor. This is the AC source symbol. We are connecting this to capacitor. This capacitor capacitance is C. And this AC source supplies the AC current or AC voltage which varies in magnitude and direction also. It does not have the current direction always like this. Periodically the current direction will be changes. Right here sometimes it is plus minus. After certain time it will be minus and plus. The terminals of the AC source will be changes regularly in periodically. Okay, right. And now I am going to derive the formula for the instantaneous current through the capacitor. Okay, right. For that, first I am going to write the AC source voltage, instantaneous voltage that we are connecting to the capacitor. Instantaneous voltage or AC source voltage. Right? What is the AC source voltage? That is the V. We can write V is equal to V0 sine omega t. This is the voltage at any instant of time or the EMF at any instant of time. This is the equation 1. Everywhere this will be same. Previously we discussed the AC through resistor, AC applied to a resistor, AC applied to a inductor. Everywhere we are applying the AC. That AC voltage is equation is the same, that is V is equal to V0 sine omega t. But the current through the circuit will be changes when you change the instrument in the circuit. For example, AC through current through the resistor is different, current through the inductor is different, and current through the capacitor is different. That means in different instruments different current passes, right? But the voltage source voltage equation is same in all. Okay, in every case AC applied to the resistor or inductor or capacitor, three cases we are discussing. In every case we took the AC source voltage as like this, it is fixed, and every time we derived the current equation. Right? Current through resistor we derived, current through inductor we derived. Now we are going to derive the instantaneous current that is passes through the capacitor. Right? And now for that purpose, everywhere we are using these two are the parallel combination, that is according to Kirchhoff law, or directly we can say that the voltage across AC source equal to voltage across capacitance. The voltage across capacitance we are considering as V suffix C. Then we can write like this, that is from figure, right? From figure, that is a Kirchhoff law. The voltage across AC source is equal to, we write voltage across capacitance. But the voltage across AC source is V0 sine omega t, and voltage across capacitance, we write like this, that is, we know capacitance equation C is equal to Q by V, right? You know C is equal to Q by V. From that, if you write the V equation, then we will get Q by C, right? At any instant the charge on the capacitor is Q and its capacitance is C, then we write Q by C. Okay, and from this we can write the Q equation, right? And then what you will get the Q equation, that is Q equation is, we take C to left side, C is the capacitance, we will get C V0 sine omega t. Now what we have to do, we want to find out the current. This is the instantaneous charge. This is the instantaneous charge stored on capacitor. That means the charge stored also changes with the time on the capacitor, right? Instantaneous charge stored on capacitor, right? On capacitor. But I want the current. When you know the charge, how to find out the current? The current is the instantaneous current, right? It is the rate of flow of charge. Instantaneous current is the rate of flow of charge. We write I equal to dq by dt, right? We come to differentiate this one. Then for the purpose I is equal to d by dt of q is already we know, that is c v naught sine omega t. In this we have to write constants outside, then I is equal to what we get, c v naught into d by dt of sine omega t we write. But what is the differentiation of sine omega t, right? The sine differentiation is cos and omega t differentiation is omega. Then we will get omega cos omega t. Okay, this is the differentiation of sine omega t is equal to omega cos omega t. Omega cos omega t. And then we write like this, v naught into this c omega we write 1 plus cos omega t we write. Okay, right. And the next step I am going to convert this cos into sine. Then for the purpose we can do like this, this c omega we can write in the denominator, that is 1 by c omega, and to cos omega t I will write as sine 90 plus theta, right? That we can also write as omega t plus 90. Then this is I is equal v naught by this 1 by c omega again goes to numerator, means we will get the same equation. And here we write the since cos theta is equal, we can write sine 90 plus theta, right? This formula we are using it here. Sine 90 plus theta is cos theta. V naught by xc into sine omega t plus 90 we write. Actually this is the current equation, instantaneous current equation. Here current equal to I equal to something into sine. If the sine is V is the voltage by, this is the resistance, voltage by resistance. Xc is the capacitive reactance. It is called as the resistance offered by the capacitor for the flow of AC. That means this is the voltage by resistance. This we can take as current. That means we write the equation for the instantaneous current, that is I is equal to I naught sine omega t plus 90, right? This is equation 2. But in this peak value of current is what? What is the peak value of current? Here we are considering the peak value of current as V naught by xc, right? Okay, this one we derived, that is in this I is the instantaneous current, right? Instantaneous current. Instantaneous current means current at any instant of time. Then the voltage equation in the sine, AC source voltage, instantaneous voltage, and instantaneous current also in terms of sine. Then we can take the phase difference. Phase difference means angle difference. Voltage angle is omega t, current angle is omega t plus 90. If you find the difference, then you will get the 90 degree, omega t plus 90 minus omega t, 90 degree. This is the phase difference between the current and voltage in the capacitor. In the inductor also we got the same thing 90 degree. Here also we got the same thing 90 degree. Okay, right. And now, but the voltage angle is omega t, but the current angle is omega t plus 90. That means current leads the voltage by 90 degree. Okay, the current angle is more by 90 degree. Voltage angle is omega t, but the current angle is omega t plus 90. That means current have more angle. That means the current leads the voltage by 90 degree, or voltage back by 90 degree we write. That means voltage lags 90 degree, voltage lags the current by 90 degree in the capacitor. This we can write. Okay, now you take the screenshot and note every point, then I will continue. Okay, the next I will write the phase difference, and the next logs are leads, and then after that Phasor diagram. Okay, then this topic will be closes. Okay, right. Okay, let us see from equation 1 and 2, right? Oh, before that I will write the peak value of current. What you got the peak value of current, right? Peak or amplitude of current. Amplitude of current just from above equation, right? That is equation 2. Then from that I naught is equal to, we write as V naught by XC, right? We can take this as equation 3, right? And the next from equation 1 and 2 we write one thing. From equation 1 and equation 2, phase difference between the current and voltage is nothing but angle between the current and voltage. Phase difference between current and voltage, what you will get, that we will get as 90 degree, omega t plus 90 minus omega t, right? Current angle omega t plus 90, voltage angle omega t, then we will get again 90 degree. That means in inductor, in capacitor, the phase difference is same. Okay, right? And the next, that means we can write from equation 1 and 2 one more thing also we write. Okay, from equation 1 and 2 we write like this: current leads voltage by 90 degree in capacitor, or otherwise we can also write like this, or current leads voltage or voltage lags current, voltage lags current by 90 degree in inductor when we connect the inductor to the not in inductor, that's we are discussing the capacitor, right? There is a capacitor. Right. And the next I am going to explain the phasor diagram, right? How to draw the phasor diagram. Phasor diagram. Phasor diagram means what? Representation of current and voltage as rotating vectors. Then how we can indicate? Let us see here. Right. For that, from equation 1 and 2 we write the equations, right? Equation 1 and 2, right? What we can write? Voltage equation we got as V naught sin omega t. It is fixed in everywhere. And the current equation we got as I naught sin omega t plus 90 we got. That means current leads, current angle is more, voltage angle is less. That's why current leads voltage by 90 degree. Now we can draw the phasor diagram. This is just x-axis and y-axis. And the next I will take the voltage angle is 90 voltage angle is omega t and the current angle is omega t plus 90. Okay, that means the current leads the voltage. Then we can draw like this. This I am taking as current. Okay, you take this as voltage, its angle is omega t. This is the voltage across capacitance, and this is the current. The current angle is more by 90 degree. The current angle is omega t plus 90. Like this it will be there. Okay, or otherwise we can draw like this. Okay, this is the phasor diagram. Phasor diagram. In this, current is, voltage is back of current, right? It is rotating in anti-clockwise direction. And the voltage angle is omega t and the current angle is omega t plus 90 with positive x-axis. We can indicate this one like this, no problem, right? And like this also we can draw. This is the current, and this is the voltage across capacitance. This is the voltage across capacitance. Okay, we can draw like this, there is no problem. And here we are indicating as rotating vectors, right, like this. You see here, in this, current leads the voltage by 90 degree. Both are rotating in anti-clockwise like this, and then the current is leading, firstly going, and the voltage is back of current, exactly opposite to previous case. In the previous diagram we write here voltage, here current, means voltage leads, current lags. Here voltage, here current we wrote, voltage leads, current lags. In the AC throw inductor, this is the AC throw capacitor phasor diagrams, either like this or like this we can draw simply. Okay, right. And the next, I am going to draw the graph, that is the VT graph. VT, V versus T, V versus T, or I versus T graph. Okay, right. I am taking the time on x-axis, voltage or instantaneous current on y-axis. Then if we draw the graph, then how you will get? First, this is x-axis and this is y. This is x-axis and this is y-axis. On x-axis it is fixed, that is we are taking the time on x-axis. The time is t. On y-axis I am taking the either voltage or current. One time I will draw by taking voltage, other time I will draw by taking current. Then if the voltage, if you will take it is a fix, that is the voltage equation does not changes, and voltage graph also does not changes. It was very simple. Right, this is the equation for the voltage. V is equal to V naught sin omega t. What about the current? Current equation is sin 90 plus, when time 0 you take, when time 0, V0 you will get 0 comma 0, it will start voltage. But when the current time 0, then what about the current? I equal to I naught, sin omega t. Omega t is 0, sin 0 plus 90, sin 90. Sin 90 means you will get 1. I equal to I naught you will get. That means when time 0, then we are getting the current as I naught. Here the peak value of voltage is V naught, and the next it will start like this. Okay, this is the I naught. Okay, this is the origin, right? And this is the graph for I is equal to I naught sin omega t plus 90. Okay, right, like this you will get. This is about the AC through capacitor. If we connect the alternating current to the capacitor, then what happens, that we discussed.